Okay, so now we're recording. Great. Now I'll go back. Okay, so for test, for number one here, the scientific method. When you're using the scientific method, actually, if I do this with you guys.
We can't see your screen.
Oh, you can't?
Not right now.
Oh, that's weird. I thought I just shared it. Okay, here we go. Okay, can you see it now?
Yeah.
Oh, that was very bizarre. Thank you. Yeah, so if we look at number one, they're asking, according to scientific method, how does the physicist formulate an objective test hypotheses? It's true for any scientist. So you always start with like an idea or a question, like you're kind of curious about something. You do some research on it, and then you construct your hypothesis. And in order to prove it, you got to run experiments. By that, once you feel like it's working, then you kind of like draw your conclusions. So it has to be B for that one. You're by experiments. That's how you would test your hypotheses. For number two, millimeters represent, well, there we go, mm to millimeters. That's easy. So that's a fourth choice. So that's just D there. And again, for this one is experiments. So number one is experiments. Number two is millimeters. Number three, all 5 darts hit the bullseye on a dartboard. So the bullseye is what you're aiming for, and they're all get going there. So you remember, if all the darts go towards one area, that's just precision. But if you're going close to where you want, that's accurate. When they're all getting there at the same time, that's both accurate and precise. This one here, what you can do is you can pull up a calculator. So we got 21.4 plus 15 plus 17.17 plus 4.003. So you should get 57.573. Now, because I asked for the correct sig figs, if you look at all 4 numbers you added up, you have to go with the one that has the least number of sig figs. That would be 15. It only has 2. So and we have to round up to that. So that's why the answer is going to be 58 for that one. Now, if you put 57.6 or something like that, 57.573, I'll give you 1 point out of 2, as long as I can see your work. So that was worth, I believe, 2 points for that one. So that's 58. Here, the basic SI units. Remember, we don't use feet at all, so A and C are out. We don't use hours for time, we use seconds for time, so it's going to be D for that one. Kilometers for distance, kilograms for weight, for mass, and seconds for time. When you're at rest, you're not moving, so 0 meters per second. Acceleration is the change in velocity. So it's not velocity, it's not displacement. Rate change displacement, that's going to be velocity, but acceleration is the rate change of velocity. And that's important because I asked a few questions about that down the road. For number 8, now we actually have a calculation problem. You have initial velocity of 5 meters per second, constant acceleration 2 meters per second squared. Was the final velocity? So I want the final velocity. So remember, let me put my stylus here. Acceleration is a change in velocity over time. You know your acceleration is 2. The final velocity we want, initial velocity is 5, and the time is 6. So if you work it out, you should get 17 for that one. So that would be 17 there. Any questions about that problem? Oh, okay. We'll keep moving. If you're falling towards the Earth, it's always going to have constant acceleration. And the acceleration is negative 9.8. But we say that the speed is increased because speed doesn't involve distance. Speed is the absolute value of velocity. So we just say it's increasing speed. So your speed's increasing, but in the downward direction, of course. So that's that one. Back to another calculation. So acceleration negative 9.81. So it hits the ground after 6 seconds. It's released at rest. So your initial velocity is 0. You want the height from which the ball is dropped. So you don't care for the final velocity. So in this case, we're using this formula. Y minus y0 equals 1/2 at squared plus v0t. We can cross that off because you're at rest. So v0 is 0. And you want the height, so we're going to solve for that eventually. Now you're going to do 1/2 times negative 9.81 times t squared, which is 6 squared. And I'll just use my graphing calculator, which I have in my backpack right here. Let's pull that out. Negative 9.81 times 36 divided by 2. So you do get negative 177. Now some people, I remember, had asked me during the test that they were a little confused. Remember what the question was asking? Well, actually, I should have been more clear. I should have asked actually what was the initial position. Your final position is 0 because you're on the ground. So actually, it does make sense I keep the answer positive in the answer choices because negative 177 equals negative y0, so y0 is 177. So that's how you actually would do it more formally. But honestly, you get negative 177, don't worry about it. You just say C. And of course, it's in meters. So that's C for that one. But you know, it is good to understand all the sign changes because you are losing height, right? You're going starting from higher elevation going down. We keep moving. We're halfway through here. For 11, you drop a camera from a 40-meter high bridge. And we did say assume the initial velocity is 0. So it's actually, but you want the final velocity. So we're using this formula now. So another kinematic formula, v squared equals v0 squared plus 2a times your displacement. Well, your initial velocity is 0, so you can cross it off. So v squared equals 2 times negative 9.81. And you're going to say times negative 40 because your initial height was 40. And your final height is 0 because you're on the ground now. So it's actually times negative 40. Otherwise, you're going to get an imaginary number, right? Now, some people, when you go about physics, not really understanding direction, and you just figure, just 9.81, the height's 40. Then you're going to run into problems down the road when you actually do have to take that into consideration. So it's always going to be consistent here and just always understand, hey, acceleration is always going to be negative due to gravity. It's going down. Your initial height's 40 and it's falling. So obviously it's a negative displacement. So you always want to think of physics in that way so you don't run into problems down the road when we actually have to, when we do have all these different things happening, all these different directions, when we have to understand what is positive or negative. 2 times 9.81 times 40, square root it, you should get about 28. So the answer is A for that one. And by the way, I mean, you know, the work obviously will help you. So if you do miss a problem like this, I mean, I'm going to give you 3 out of 4 points as long as most of the work's fine. You don't necessarily have, well, actually, I think for the next test, I will require you to show work. I'll probably tell you which problems because obviously I want to make sure you're doing it. So, but for this test, that's fine if you didn't have work and you had the answer. A lot of it's calculator work too. So clear that. We'll keep moving. Number 12. Okay, 12 and 13, some of you guys have problems with. And I will actually give some partial credit here. So I do have to go back, even for those grades I've updated. If you got at least one, so if you at least picked one of these correct, but you picked like an extra choice and it didn't work, I'll give you half credit. So here's what I mean by this. So there are 3 options. So all 3 could be true. 2 of the 3 could be true. 1 of 3, or none of them could be true. You could just leave it blank. That's also a possibility. But actually, I think it required to give an answer. More, I have to double check how I set it up. But I guess you could have left it blank. But here's the deal: you're going around a track. Say you start here, and you're going this direction, and you end at the same place. So clearly, you did not change position. There's no change in position whatsoever. Remember what velocity is. Velocity is the change in position. So your displacement is 0. So definitely this is true. because you did not change position. You're getting back to the same place. You traveled once. That's kind of the key phrase. So if you said that, I'll give you at least 1 point. Now, so that's it. There's nothing else that's true. If you put another choice, and of course you missed a problem, the system gave you 0 out of 2. I'll give you 1 out of 2. I'll go back and update it. Now the average speed, well, no, you're moving, so your average speed is not 0. So clearly you're moving around this track, and it's constant speed, so that's not true. The acceleration is 0. Some people said that if it was a straight track, yes, because you're going to the speed, so the velocity is not changing. Remember what acceleration? Acceleration is velocity, change in velocity. The change in v over the change in time. Velocity is speed and direction. Now your speed is the same, true, but your direction is not. Because the direction is changing, because you're moving. I mean, you're sorry, not moving. You're turning around. So there is actually a change in velocity. I mean, yes, the magnitude is the same, but the direction is different. So you can't say the acceleration is 0. There actually is acceleration when you're actually moving in a circle. So that's why it's just the third choice. And the next one's kind of similar. So which of one must always be true? Well, of course, if your speed's constant, your acceleration is 0. We know this. So that's true. If acceleration is constant, no, we don't have to be in a straight line. It could be moving in a circle. If your acceleration is 0, then the speed, oh, wait 1 sec, hold on. I lied. It was the second choice, that's what I meant. Sorry, if your acceleration is 0, yes, your speed is constant. That is true. If you have 0 acceleration, you're moving at the same speed. The third one's not true. Your speed is constant, but who cares? What if you're turning around? Or what if you're turning left and you keep the same speed, or turning right? You do have acceleration because you have change in velocity. So a change in direction is a change in velocity, which is a non-zero acceleration. So if you missed that, just give a brief explanation, and that's why I'm recording, so you can watch this over again. 14, now we get some more calculations here. Starting from rest, accelerating 5. So we've kind of already done this already. I mean, I think at this point we kind of know, and they want to know how long, so they want the time. So we can kind of just sort of just go straight to this. 200 equals 1/2 AT squared. Your A is 5. And you just solve for T. And I do want round to 1 decimal place, so the answer would have been 8.9. If you were close, if you actually put like 9.0 or something, I don't know. I'll look at your work and I'll give you 3 out of 4 points. But you do have to make sure you're rounding correctly. And the reason I say don't state the units, if you did put the units, it actual score is incorrect. I could, I guess, change the system so that it takes, looks at a partial, answer. But I try to have it in the exact form when it scores it. So I always kind of go back and update your grades if things are a little off. So that's number 14. Let's take a look at 15. Clear our drawings. Okay, so now we have one with angles. Initial velocity of 10, launch angle 30. Calculate this whole time, flight the ball lands back on the ground. So if you land back on the ground, there's no change in vertical displacement or vertical position. So y minus y0 is going to be 0. You're doing 1/2 times negative 9.8. And we're trying to solve for time here. So t squared. And then your initial velocity in the y direction. So you want v0 in the y direction times time. So if you're launching at 30 degrees like this, and that's 10, I want my initial velocity in the y direction. So that's going to involve a sign. So you're going to have 0, because that's your vertical displacement, equals negative 4.9 t squared, plus 10 times the sine of 30 degrees, because that's going to be your vertical velocity, times time. Now sine of 30 is actually real easy. That's actually just half. So it's negative 4.9 t squared plus 5t. You can factor out t and work it out. If you factor out t, because remember you have 0 on the other side here, so you have the liberty to solve by factoring. It should be close to 1. So it should be close to 1. So the answer would be C for that one. Okay, you've got 5 more here to go over. Clear. Some of you guys said upward or gave a different answer, and I can't really give partial credit for this one. The answer is A. Well, actually, the answer choices were mixed up, just so you know. So I shouldn't say A, just G downward. I didn't mix up the question numbers because that just would make grading for me harder when I do that, because then I don't know what you saw on your end. Or actually, I think I do, because it does show me. But regardless, I did mix up the choices. Acceleration is always pointing down. Always, 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 always. It's always going towards the center of the Earth, never up. So some of you guys, I think, misconstrue that with velocity. The velocity is 0 for sure when you're at a peak, but your acceleration is constant the whole time and it's just going downward. So that's just that one. Don't want to overthink that one there. Here I'm asking for the speed at t equals 3. Remember, speed is the or velocity is the slope of the tangent line of a position graph. So this is a position graph, of course. And here's 3, and I want the slope of the tangent line there. Unfortunately, that's just a line, not a curve, so that's really easy to solve. Just find the slope of that. You're going down 2, right 1. Just give me -2 meters per second squared. Sorry, -2 meters per second. That's all.
Mr. Omar,
Can't speed not be negative?
Yeah, actually, I should have said velocity.
Oh, okay.
That's
Oh, you got me on this one.
Yeah.
Okay, we have an inconsistency. I wanted velocity. I should have put velocity in the question, but the answer choices have V in them. Yes. Okay. So if you did put 2, I'll give you full credit. I'll go back. Let me. You. Good job, Sacha. You totally caught me on that one there. So this is number 17. So I'll give answers for both. So physics. I'm putting my little notebook here. So probably during our break, I'll maybe update grades. -2 and 2. Okay. Yeah, I do have to. And I think maybe it's worth 4 points. If you had some work to show, but you're kind of on the right track, maybe you made a little, maybe you counted the slope wrong. I don't know, or you counted the rise and run wrong. I don't know. I might give some more credit, but yeah, actually, I should give full credit for both answers. So actually, a good catch there. Okay. Let me clear. Let's keep moving. Next one's another diagram. Okay. So here we have velocity. And we're asking for the displacement. You're looking for the area from 3 to 5. So that's all you're doing. Straight up, you're just doing area. 1/2 times base times height. And just get 2. So that's D. That's all. That's all you have to do. It can get a little more confusing if I did ask, hey, find me the displacement from 1 to 5 or 2 to 5. Then you actually have to count anything below the x-axis being negative. We haven't really talked about that. We'll maybe have that discussion later. But for now, because displacement is a vector quantity, it does involve direction. But because when you're below, that means you're going the opposite direction. But regardless, 3 to 5, just 2. So it's 2 meters. And again, for those who've had pre-calculus last year, you're going to do a lot of this stuff in the fall in calculus. So I'm kind of, giving you an early start on this stuff. Okay, 19. Okay, this one, you throw your graduation hat up in the air with a speed of 5 meters per second. Obviously, it's going to slow down. And when you do hit the height, your final velocity is going to be 0 when you're at the maximum height. So we have velocity, final velocity, initial velocity. We want time. And we know acceleration, of course, is -9.8. So there we go. Acceleration is change of velocity over time, -9.8. Your final velocity is 0. Your initial velocity, of course, is 5 over time. And solve it, and you should get something close to 2. Yep, you get 1.96, I think. I stayed around to the nearest, around the 1 decimal place, so it should then be 2.0. If you got 1.8, I'll look at, if you missed it and you're close, I'll give you some points for that. But I think I was looking for 2.0 as the answer for that one. Okay, and the last one. Clear it. Okay, and again, like this is worth 8 points. So you know, if you had missed this problem, I think for a handful of you I did update the grades. Again, I haven't done it for others. So don't worry if you missed it. If your work is fine and you made one little stupid error and it caused you to miss 8 points, I will give you probably 7 out of 8 points. That will make a huge difference in your grade. So don't worry if you got scores in the 50s or 60s. I think when I update, your grade will improve. And then there's test corrections too, by the way. And I still have to go back and give you credit for all the other stuff. So it'll all bounce itself out. But remember, we have to go through this whole process. We have to do a vertical analysis and a horizontal analysis. So solving for the time. So we do have to get the vertical component of the velocity. And we do know that the final position is going to be -20. So initially starts at 0 and goes down to -20. So, you know, you're doing y equals 1/2 at squared plus v0 in the y direction times time plus y0. So we do y minus y0, 1/2 -9.81. That might, if you did -9. I think it'd still be okay. If you're a little bit off because you did -9.81 or -9, I'll take a look at it. Let's see if that causes a major difference. And then that's going to be your v0 in the y direction is 25 times sine 35 degrees. I had one student who actually made a little bit error there and actually did accidentally did 30 degrees. You do that and you get the rest of the problem right. I'm getting a 7 out of 8. Don't worry, you'll be fine. So 25 times sine of 35 is 14.34. That's the other thing too, is that if you're rounding a little too soon, that can impact the results. And of course, that's -20 equals -4.905 t squared, mind you, plus 14.34 t. Move that over to the side. And then you could use Desmos at this point, or quad form. I'd probably use Desmos if I were you. Plus 20. Yeah, and if you plug all that in, let me actually go to Desmos right now. So y equals -4.905 x squared plus 14.34 x plus 20. Oh, there we go. So you have a negative answer, which we'll discard. And you have this one, which is 3.955. So if you have 3.96, which is what I wanted, that's great. If you were a little more accurate here, 14.34, sorry, that would be 394. You still have been okay. Wouldn't have mattered. If you did -14.3, yeah, then you're gonna be a little off. And then, so I probably should advise you guys to round your velocity to at least 2 decimal places. Don't worry, if you did 4.9 here, you still would have been fine. But round out a little too soon does cause it to be off a little bit. So I'll take a look at it if that happened to you. And then once you have the time, then you can actually plug it into the range formula. So let me close this down, leave. And yeah, the range formula is just this. which is x equals v0 in the x direction times time. V0 in the x direction is going to be 25 times the cosine 35 degrees times your time, which we have 3.96. And of course, you have 3.95. You're going to be off a little bit. 25 times cos 35 is 20.4788. Again, if you round that too soon, that's also going to be a problem. So I probably advise that you just kind of leave things in the calculator. So times 3.96, you should get 81. And I wanted the nearest whole number to kind of avoid that from happening if you had rounded a little too soon. I think it still would have been okay. Yeah, you should still have it 81 if you round that a little too soon. So time was 3.96, and here that was 81. So yeah, so that's the whole test. We can clear this. Say finish the test. Doesn't tell my score, but I'm pretty sure I got all that right. So so that's the test. So feel free to watch this recording again. I'll upload this after class is done. And test corrections will be due, and not everyone has to do it. If you got like a 97%, and you're like, I don't want to do it, then don't do it. That's fine. You're fine. But if you got like maybe 80 after I do after I update the grades, I'm gonna try to update the grades during our break today. Whatever your grade is after I do the update, and I'll email everyone letting you know that the update has been done. Then I'll return half the points back. So say after the update you get 80% and you do video test corrections, I'll give you 10 more points back. And I'll put a link so you guys can actually see that. And what I mean by video test corrections is you probably, I'm trying to think what's the best way to do this. You could probably do it on Zoom, maybe. I'm not sure because all you guys have Zoom accounts, so you might be able to go on Zoom, share your screen, and then do that and record it that way. That might be a possibility. If you're not comfortable doing that, you could obviously just go to Schoology and print your test, and then you can kind of then just talk about it, or you could have your camera out and have your camera recording. Like you could take your cell phone here, right, and kind of kind of talk about it. So I'll accept it a few ways, and I'll put some details. You can like print and write everything out and then talk about it, or you could just handwrite stuff from the website and say, okay, here's what I did wrong, and record as you're talking through your mistakes. Or you could just pull up the screen and just record as you're going through the screen. Either, I don't really care, but I do want to record it because I think it's a little easier. Plus, I get to hear you explain things. That's also a good thing. So I do want that. And then you could just go to YouTube, and you'll see all the weird stuff I watch on YouTube. I watch a lot of 80s music. And you'll probably see Peppa Pig or Elmo. And my 7-month-old, I do have like white noise. I don't know what this is. I don't know why that's there. Comedians, I do watch some interesting movies like No Country for Old Men. It's a good one. A little violent. Some sports, news. Yeah. Oh geez, that's crazy. Anyway, but yeah, I digress. If you go to YouTube and click on upload video, then whatever device you have, it should save as an MP4 file. And just click on that. It should work, and then share with me the link. If you run into problems, let me know. Then maybe we could just sort of meet before class, and you can kind of just play the video for me during a Zoom call. That's fine too. But if you can upload, this might be a little easier. So that's how I'm gonna have you guys do it. Again, it's optional. You don't have to do it, but it is a great opportunity for you to learn from your mistakes, right? To test our learning instrument, and at the same time, you can boost your grade. Okay, so I think I'm done talking about all that. Any questions about the test? Nope. Okay, great. So, and I think that's what I'll do every Monday because we don't really have too much to talk about because I'm only giving you guys like really the video to watch on Sunday nights. So, yeah, I think that's kind of good to spend the first 30 minutes. So, if if the test goes well for you, I mean, if it goes well for everyone, then I'll probably maybe not spend as much time. Maybe I'll go through a little more quickly. But I know the first test, especially if it's subject like physics, I think it's kind of good to spend some time talking about these tests. And I'm going to design most of the tests in a similar fashion. So, and I think pacing was fine. I think most people got it done within the time limit. So, but if you feel like you need more time, just let me know. Okay, so week 2, Saturday night homework. So again, watch flying video lessons. There are 3. We'll quickly talk about that in Google form. Submit your problem sets. Some of you guys have done it. If you haven't, I did extend that till tomorrow, so you can do that. You know, and again, don't worry if you didn't get all of them done. Just show me a picture of a couple problems per section. And we didn't do 1/7, so basically, you could send like a few images of all that, and I'll just take a look at it. And in the lab 1 worksheet, we didn't do all that either. Just show me what you got. That's fine. We'll be more formal with the labs this week. And actually, we're not going to do any labs today because we do have to learn about friction. We're not going to get into friction until tomorrow. So we'll start the lab tomorrow. But let me pull this up. Actually, I do need to go to my Google Drive. Okay, let's go to physics. There we go. Let's pull up Sunday, June 14th. Great. One person has a submitted response, so please do if you're that one person. So Sir Isaac Newton, yeah, he was a brilliant scientist. I would agree. Just he did invent calculus. So calculus and physics are very, very intertwined for obvious reasons, because the person who is considered the father of physics also invented calculus, so it kind of makes sense. Yes, very popular in the late 17th century. Just considered very influential in the way we look at physics now. And a lot of things are derived from his formulas. So like when you look at electricity and magnetism, when you start looking at optics, like things that are not necessarily dealing with motion, the way we see motion, a lot of things are derived from his equations. So he is very important. Newton's first law, those are things you can easily just look up. And the video talked about it. Yeah, for every, well, actually, sorry, I was going to quote the third motion. This is a good one here. Newton's first law of motion states that object in rest will stay at rest. So like, for example, you can see here my, all the stuff here on my desk. You see my calculator, my stylus, my planner. We're not moving right now, so they stay there. There's nothing that's acting on it. But if I do decide to push them, so like for example, if I kind of do this here, now I'm pushing these things because I'm applying force with my fingers. And of course, there is a force that's kind of holding things back a little bit. So I have like this red wooden table. So there's something called friction that's kind of making this a little bit harder for me to push it. If I were to put like some sort of cleaner on it that makes it more smooth and slippery surface, yeah, then it's going to move more easily and it's more slick. So those are things that we'll talk about. But an object in motion will stay in motion unless an unbalanced force acts upon it. Usually that might be like friction or something else, or something holding me back. Applications, yeah, soccer ball will be at rest unless activated and you kick it, great. Or the wind might move it. Actually, my parents bought my son an inflatable, actually, I'm not sure if you guys can see my backyard there. Okay, you can't really see it. Maybe a little later maybe I'll show you guys a picture. But we bought my son my parents bought my son an inflatable shark for the swimming pool. And if it's windy, it's probably going to move, right? So that's a force. Obviously, if it's not windy, it's just going to stay stationary. Actually, it's in the water right now, and the water is kind of moving a little bit. There's a filter. The shark's going to move a little bit. Lost soccer ones, that's interesting. Car, yeah, it doesn't turn on until engine compels it. Yeah, and then you have to step on the accelerator, and there's a force being applied to it. Hockey pucks on ice eventually will stop because of friction. Yeah, but it does move pretty easily because ice has very low friction. So all fantastic examples here. Yeah, we're going to talk about actually second law today as well. I only showed a video with the first law, and I'll give videos on the second law and the application of it. But the second law is force equals mass times acceleration, which is one of the most essential formulas in physics. So mass, it means, you know, you're measuring how much matter something has. Acceleration, we already know about that, the change in velocity. So when you're looking at those two things, you're going to have force. Now, if you have a constant velocity, mind you, and maybe that's the question I should ask for the Google form tonight. If you have a constant velocity, you have zero acceleration. So guess what? You have zero force. Now, of course, if something's moving at a car's moving at 30 miles per hour consistently in a straight line, and it hits you, yeah, you're probably going to die. you're not going to, or you're going to be seriously injured. That's a different thing called momentum. We'll talk about that next week. And there's also something called energy too. Well, actually, energy wouldn't make sense because that's force times distance. But yes, when you're dealing with collisions, yes, you are going to, or if you drive a car at a constant speed down the road, another car is going the opposite direction at a constant speed, and you guys hit head on, that's going to be a very catastrophic accident. But again, that's momentum. That's a much different thing. Force involves acceleration. So if you have zero acceleration, so if you have constant velocity, you'll have zero force. But things here, if you push a shopping cart, yeah, like let's say you're trying to race somebody all of a sudden, like then you start pushing it really fast, there's force there. Or right, if you deadlift, like, because you know obviously it's motionless and you lift it up, great, that's force. Same thing. If you're kicking a soccer ball and it's going towards a goal because it's falling because of acceleration, that's force, right? Throwing a football and trying to catch it, that has force because it is going to slow down eventually. But of course, initially you're throwing with some zip too. So anything that has mass and acceleration will experience force. And then looks like you guys prefer, okay, July 3rd it is. I guess you guys want to get a head start on the, cool, works with me. I think Monday people just want to get back. So if you happen, I mean, I think people are starting to travel again. People are starting to, you know, go visit other places. So yeah, just make sure, well, it's online anyway. So if you stay on vacation, I don't care. But we are going to be on July 6th. So we'll take July 3rd off. But, you know, don't be on the road driving back from Tahoe or something like that or somewhere else on the Monday morning because we'll have class then. So just make sure you're settled somewhere. But yeah, we'll skip the 3rd for sure. So I'll make an adjustment. I don't know what, I think that's week 4. Let me see here. We're week 2, sorry, it's week 5. No, sorry, that is week 4. Yeah, week 4, I think we're covering, I think circular motion. So I might cut that unit short a little bit. So, okay, cool. All right, so majority wins on that one. All right, so now we're gonna get started by doing a lesson. So we're not doing a lab today. So instead, we're just gonna do lessons on force. We're gonna do 2 worksheets. Let me show you the worksheets we are working on. It's gonna look just like this. So 2.1 and 2.2. And those are actually the filled out ones. So let me pull up the student versions. Nope, that was last week. Let me close that down. Don't need these here. So let's open up 2.1. And let's open up 2.2. Okay. Now another thing too that we need to discuss. So the lab is going to involve friction. And there's going to be a simulation again. We are not ready to do that today. We need to cover 2.3 and a bit of 2.4. So that's when we'll open up the lab tomorrow. But for today, we're just going to do stuff on 2.1. So I'll probably lecture us for maybe about 10 minutes or so. Probably not that long. And then I'll give you guys a chance to do some problems, maybe about 20 minutes. I'll have you guys in breakout rooms. Then we'll talk about, they'll do a break around 11:30 for lunch. And then we come back from lunch. We'll talk about 2.2. I'll do a little bit of a lesson on that, maybe about 15 minutes or so. Then give you guys a chance to work on this stuff. And then probably we might end a little early today. Maybe we'll end around 1-ish. We'll see. So give you guys a head start to do your test corrections, as well as more videos and discussion topic. I'll have that established as well. So there's a few things, and then of course the problem sets and the labs if you didn't finish from the previous week. So because I know you guys have quite a bit of other work to get caught up on. So anyway, let's get started. So I'm going to get my status out again. So let's talk about all this fun stuff with Newton's first law. Okay. So when you're dealing with a force, right? Usually the way you think of a force is anything that involves kind of like a push or a pull. So if you're pulling on something, push something, that's going to be a force because you have mass, right? Or whatever you're pushing has mass or pulling, and it's going from rest to velocity. So that's a change of velocity. So there's acceleration. So think of it this way: whatever object you push/pull has mass and was probably at rest before you pushed/pulled it. Say, for example, you open a door, like one of those swinging doors, right? So it probably wasn't moving initially. You push it or you pull it. That door has mass. They went from 0 velocity to a non-zero velocity. Now you got to change in acceleration. So it's all very conceptual. So it's a non-zero acceleration. And it is a vector. Now, first of all, just to know, mass is a scalar. But acceleration is a vector because it has direction. And because that's built into the force formula, because force equals F equals ma, as you see right here, then force is a vector. The units we use is called a Newton, which obviously is named after the father of physics and his laws. So it's a Newton, and a Newton, just so you know, is a kilogram times meters per second. This is kind of a must to know. I'm going to really have to emphasize units here because that kind of helps you to really understand all the other stuff we do down the road, to really understand all the other units. And when you do the calculations, it helps to actually know the units because then you can make more sense of those calculations. So really make sure you know your units. Usually it's measured by a spring scale when you're measuring force. So let me ask you guys this question. Say we go to a grocery store. Okay, so go to the grocery store, and actually, hold on a sec. Before I do that, can I erase all this? Yeah, great. I will go and erase. Now, yeah, like you look at a spring scale like this. Oh my God, it's $1,000. Geez. Okay. Good thing I don't own a grocery store. But you need something accurate because you don't want people to shortchange you when you're they're buying produce. So when you're putting the thing on here, so say you're putting like apples or bananas, I don't know, whatever you're buying. What is it usually what units do you think these scales tend to give? If you go to like Whole Foods or Safeway or any store nearby, what do you think the units are going to be for that? Anyone can chime in, or did someone put a chat?
Pounds.
Pounds, it's going to be pounds, exactly. Oh. Okay, why is it? I don't want the survey monkey bot. Okay, anyway. Yeah, it's going to be pounds. Pounds, believe it or not, is not mass. It's actually force. Pounds is force. So what's happening is that you're putting something on here that has mass. Say put a little apple here, right? But also it has acceleration due to what? So if you think about it, you drop the apple in there. What's weighing the apple down? What's true about gravity? All this? I mean, I'm sitting in a chair right now because the chair is on the ground and the chair is acting against me. But if someone took a chair from underneath me, I'm going to fall down. My butt's going to hit the ground, right? Because of gravity, right? So, so it's actually so these spring scales are actually measuring force. They're not measured. So when it goes to how much that weighs, weight is actually a force. Believe it or not, weight is force. It's not mass. If you put yourself on a scale and you weigh yourself and it gives you in pounds, that's actually going to be that's still a force because your body's weighing it down. So yeah, it's kind of interesting. And then there's a conversion when you go from pounds to kilograms, obviously, kilograms is still mass, but that's still going to be a force. Okay, let's go back again here. Okay, so let's talk about first law of motion. Then we'll talk about inertia, then we'll do second, third, do example problem, then I'll let you guys do some practice. Okay, let's see here. Hold on a sec. Okay, so an object at rest remains at rest. I think you guys had answered that. That's great. And an object in motion remains in motion at a constant velocity, meaning zero acceleration, unless acted upon by an external force. And force has non-zero acceleration. Like, for example, if you open a door, now you're the external force, right? Property objects to remain in constant. So we're defining inertia now. So inertia is something we kind of consider to be the property of an object that remains in constant motion or rest. And mass is a measure of inertia. So inertia is kind of this interesting physics term. It really just kind of, you could kind of think of it as the potential to do force. I think you could say that. So there's a potential to have force. So if you look at like a really big football player, yeah, he probably would have a lot of inertia. You'd probably be a little bit threatened by his, because he has the potential to bring a lot of force, if he's like running really fast with a football. So inertia is more just a property, and just its mass is a measure of inertia. So we'll get into more of those details later. Second law, now we're going to talk about that. The acceleration of a system is directly proportional to and the same direction of the net force and inverse proportional to mass. So you guys might have remembered learning about this in Algebra 2. So this is called direct proportion, and this is called inverse proportion. You might remember this from Algebra 2. So you're told that acceleration is directly proportional to force. Well, duh, of course. Here's force is acceleration. So it follows kind of this formula here, where your A or M is your constant. So if you have a mass that you kind of just know is not going to change, then yeah, force and acceleration are directly proportional to each other. Whereas acceleration and mass, if your force is a constant, then you could think of your acceleration and mass being inverse proportional. So if you have more acceleration, then you have a lower mass, or vice versa, if force is a constant, if force doesn't change. The mass acceleration will be going inverse to each other because they're being multiplied together. So I know I'm kind of dissecting this a little bit. Maybe I'll give you a little more detail than you really need to know. F equals ma. We'll just keep it simple. Just know that and you'll be fine. So F equals ma. Let me change colors to green. Third law of motion. I accidentally said that, was going to say this earlier. It's basically for every action is an equal and opposite reaction. So whenever one body exerts a force on a second body, the first body experiences force is equal in magnitude and opposite in direction. So you can kind of think of it as like myself sitting on a chair, right? Obviously, I have mass, and my body's being weighed down by the exertion due to gravity, but the chair's acting against me to keep me propped up. So that right there, the act of me sitting on a chair is the third law of motion. You could also think of it like if you make contact with a baseball, obviously you're swinging the bat, so there's a force there because the bat has mass and it's accelerating. The ball is coming at you, that's also has mass and accelerating. So you kind of would think that, okay, when the bat makes contact with the ball, you kind of expect the bat to kind of somewhat recoil a little bit, or kind of, I mean, you do swing through it, but it's going to kind of have this like reaction where it's kind of going backwards a little bit, and the ball, of course, going forward. But for every force, there's an equal and opposite reaction force. That's what we kind of expect. So those are the three laws of motions. You'll have videos on the second and third laws throughout the week, and we'll talk more about it down the road. And there'll be some, the discussion topics will probably be in relation to these three. I think that that's kind of like the key thing we're doing. We are going to get into energy as well, though. So looking at, actually, no, sorry, we're doing energy and momentum next week, sorry. So we're not doing energy, we're just sticking with force, because that's a lot. So yeah, let's get into, so force is the main thing for this week. So most likely discussion topics will be on the first three laws of motions, and kind of give examples, and then you guys will engage in conversation about that. So I'll make sure that's up also before 2 p.m. So let's look at this. A football player named Al is blocking a player on the other team named Bob. Al applies 1500 force on Bob. Bob's mass is 100 kilograms. What is his acceleration? So first off, Al's going that direction. Bob's going that direction. So he's applying 1500 newtons. And here, all we know is mass is 100 kilograms. So what we do know is that the force of Al equals the negative force of Bob. This is the third law of motion. The force of Al is the negative force of Bob. And Al's force is 1500 newtons. And force equals mass times acceleration. So negative 100 times his acceleration. His acceleration is going to be negative 15 meters per second squared. And by remember, a Newton was a kilogram times meters per second squared. I'm not sure if I accidentally wrote meters per second. If I did, please correct that. It should be meters per second squared. So if I did make that, I don't remember if I did, but it should be meters per second squared. You could just say it's 15 too. I don't really care if you give the direction so much, but because you could also say this too. That's also true. The magnitude of the forces will be the same. So the absolute value, so you can kind of keep it positive if you wanted to. The size of Al's force obviously was 1500 newtons. If Al's mass is 75 kilograms, so 75 times A equals 1500. So his acceleration is 20 meters per second squared. So hopefully that kind of makes sense for that one. So any questions about these first three questions? Hopefully those seem pretty straightforward. Okay. This question here, and then I'll let you guys do some practice problems. A 0.04 kilogram golf ball hit by a driver. By the way, not someone driving a car, like an actual golf club called a driver if you don't play golf. Can accelerate from rest to 6 meters per second in 1 millisecond. I think it's a millisecond. While a driver's in contact with the ball, how much average force does the ball experience? Well, I need my acceleration first. So remember, force equals m times a. My mass is easy, 0.046 kilograms. And just like math class, physics builds upon itself. So remember how we found acceleration, right? There's a change in velocity over time. So it started from rest and went to 6-7 meters per second. So 6-7 minus 0. And this in 1 millisecond. So you have to do 0.001 seconds, mind you. So you do have to be mindful of the units. That's why we spent all that time. You can't put 1 down there. You got to put 0.001. It's milliseconds. So the acceleration is actually going to be 6-7 divided by 0.001. So it's crazy fast. 67,000 meters per second squared. And that's what I put over here. If I multiply the 0.046, so it's about 3,082 newtons. Which is a lot of force, which is why you never ever stand next to someone hitting a golf ball. That would not be a good idea. Okay. So that's the average force it experiences. So that's kind of some stuff you'll be working through. So let's do Yeah, let's do 2, 3, 4. I think those are good discussion topics. So I'm gonna have you, talk about that with people in your breakout room. And then we'll probably do maybe just give me a sec here. I'm trying to think about a good one. Maybe we'll do 6 and 7. And 8. Yeah, I think those are 6 good ones to do. Then we do more during the break. So yeah, you guys are gonna do 2, 3, 4, and 6, 7, 8. So 2, 3, 4, 6, 7, 8. I'll give you guys 15 minutes to do those problems. So you'll kind of write stuff out for 2, 3, 4. And again, you probably want to get a notebook. I was trying, because you're not gonna have enough room to write these on these worksheets. So having a notebook or a notepad where you can like just be organized by like, okay, here's 2, 1. So, or even like something like this, or like a notepad like this, might be good. Just have it all organized. So 2, 3, 4, 6, 7, 8, and then we'll discuss after 15 minutes, and then we'll do a lunch break. So I'll put you guys in breakout rooms right now. And we got 12 people. That's perfect. Let me stop the recording.